Hi, welcome back to Online Statistics. Today we will be covering chi-square. This is lecture 11, and there are a couple different types of chi-square that we will talk about. We'll first talk about the type of variable that we use a chi-square test for, and then we'll talk about the different tests of chi-square, the goodness of fit test and independence test. Then I'll do a review of the chi-square statistic. You'll be familiar with it by the end, and we'll look at how articles report the chi-square statistic, what it means when they're reporting the statistic. All right, so first, the type of variable. You remember back at the beginning of this class when we talked about different variable types. When you have a variable or multiple variables that are only nominal, so only categorical, then you would want to use a chi-square. You might be thinking, well, if it's only a categorical variable like hair color or eye color or blood type, or sex, male or female, if it's only a nominal variable, then what numbers do you use? So in chi-square tests, the numbers we're using are just counts of the number or the counts of each individual that falls into each of those categories. So we're doing test statistics with the counts that fall into some different category. So we could count how many males and females, and our one variable there would be male or be sex with two levels, male and female. All right, so the first type of chi-square test is used when you only have one variable, one nominal variable. And that chi-square test is going to test some sort of predetermined fit of the different categories of that variable. So for example, I might want to know if there's a difference in sex that signs up for a Psych of Women course. Okay, so I'm wondering, okay, do more men sign up for Psych of Women because maybe they're interested in learning about women, or do more women sign up for Psych of Women? And so I might go out and collect data from a classroom, and here's a categorical variable, sex, enrolled in this classroom. I have two levels here, male and female, and I'm going to break up the counts of individuals in the data I collect, individuals in the class, into counts of males and counts of females. Now, the question we're asking is there a difference of counts in those two categories, male versus female, or does it fit what we would expect if there's equal enrollment? So here, it's really clear the percent that you would expect to fit if there's equal enrollment of males and females is 50% in each group, 50% males, 50% females. So suppose you collect data on 100 students. Your expected values are 50 males and 50 females if your null hypothesis is true, if the fit is good, if there's no difference between the categories. So this is a fit we're expecting, the 50% that we're testing. Now, what we observe, with only taking in data from 100 students, you might get 51 men in the class and 41 females in the class. That's the count of men and women, 51 and 49 would add up to 100. Now, if you get that, would you jump to the conclusion that in the population, remember, we're still hypothesizing about the greater population based on this little sample of 100, we're hypothesizing about all of those Psych of Women classes out there. So based on this difference of 1, would you expect that in the population there's really a difference in having more men than women in these classes? You probably go, no, it's likely you would get that difference just by chance, just by the classes that you ended up getting. You might go and take another sample of 100 and find the opposite, that there's one more woman in the class than men. So we go, how big is the difference of what we observe? That's what the O stands for on the formula. What do we observe? How big is the difference of what we observed from the count that we expected to get if the groups were equal or they fit our pre-calculated fit that we expected if the null was true? So this chi-square statistic, you can see the little x squared, the chi-square, that's the symbol for chi-square, and the formula is just the sum of observed counts minus the expected counts squared divided by expected count. So in our condition, if we had 100 students, we were testing the fit of 50% men, 50% women as our null, we would expect to get, out of those 100 students, we would expect 50 men. So we would take how many men we observe, that's the O. If we got 51, it would be 51 minus 50, square it, take how many women we observed, minus how many we expected. So if we got 49 women, that would be our O for the women, minus E, the 50 squared. You add, divided by the expected for each of those. So you divide by 50 for each of those, you add them up, and that's your chi-square value. It's pretty straightforward. So I'm going to give you an example on the drawing board of this chi-square goodness of fit. Now I like to look at the question you're asking. Are there more men or women in this class? So you're asking, sex, does it vary differently than what would be expected? So if you're doing the expected in each of these is 50% and 50% or 0.50 for each of these. Now, once you have this expected frequency or percentage or probability, you can just multiply this by the total n. So if the total n in your class, instead of 100, if your total n was 200 for your sample, then how many men would you expect here? Your expected value for men would be 0.50 times 200 or 100. So your expected value is 100. Your expected value for women based on this probability is 0.50 times 200 equals 100. So you expect 100 men, 100 women in each or in the class total in your data set that you're collecting from Psych of Women classes. You'd expect, if you have an n of 200, 100 to be in each of those categories. If you're testing the goodness of fit of 50% and 50% in each of those categories. So then you go out and you collect the data, you get the 200, your sample of 200, and you observe different values. So you go, and the men in here, you have, let's say you have 20 men, and let's see, that would leave 180 women. So this is what you observe. Those are your observed values. Now to calculate the chi-square, you need to take, so I just put O for observe. That's not a 0, don't confuse that with 0. So it's your observed value. So then with your chi-square statistic, you are going to end up adding up your observed minus expected. So for men, you take observed, your observed was 20. 20 minus expected, your original expected was 100. And you are going to square that, divide by your expected, which was 100. And you're going to add that to, since you have the sum at the beginning, you're going to add that to the observed for women, which was 180. 180 minus your expected for women, which was 100. Square that, divide by the expected for women, 100. And once you get those, you add them up. That's your chi-square test statistic. So we'll go ahead and calculate this. Go ahead and add this up, square them, calculate your chi-square. Now, we'll talk in a little bit about how, once you get this chi-square value, once you've calculated this, added it to this, and you have added it up to get your chi-square value, how to determine whether that chi-square value is significant. There's a distribution for chi-square, how big of a difference or how big of a chi-square value you would expect to get by chance at different degrees of freedom. Now for this goodness of fit, your degrees of freedom are just the number of categories you have in your variable. Remember, we're only using one variable, but it can have several categories. Here we only have two categories in our variable, men and women. So our degrees of freedom equals 2 minus 1. The number of categories minus 1. So here you would use your chi-square table. In the back of your book, you would look at the degrees of freedom of 1 and look up your chi-square value to see if it exceeds. Now, since we're squaring values here, think about ANOVA where we use squares. You're not going to end up with negative chi-square values. So you're not ever going to get a chi-square value below 0. The chi-square values are always going to be above 0. So you're only going to cut off when you go to the right of your calculated cutoff criteria for this degree of 1 degree of freedom in your table. You'll mark that on here. And then you'll take your calculated test statistic, your chi-square. If this test statistic goes past this direction, past your cutoff value based on this degree of freedom, then you reject the null. If it's closer to 0, the difference between your observed and expected squared, if it's below your cutoff, then you retain the null that you say it isn't different. If you retain the null in a goodness of fit chi-square, you decide that what you observed, your observed values weren't far enough from the expected values based on this percentage or probability. They weren't far enough to conclude that you got a difference that wasn't based on chance. So you conclude that probably your small difference was just based on chance, that this doesn't really exist a difference in the population. If you reject the null, then you decide your observed values were far enough from your expected values that the difference between your observed and expected was probably a difference that reflects a difference in the population. And you conclude that the population does not fit if you're rejecting the null. It doesn't fit this 50%. Maybe there's fewer percent of men who enroll in these classes. All right, hopefully that makes sense. I'm going to give you one more example on goodness of fit. This example I wanted to give you, we're not going to do the calculations, but I wanted to give you because the last one was 50% in each group. But in my classes, I like to do a little study with horoscopes to see if horoscopes work or not. And sometimes you don't end up with the expected values in each category being 50%. So what I do with the horoscopes is I print out, and now that I tell you this, you're probably all going to guess when I'm going to do it and go look at it the day before. But I print out the horoscopes for a day, and then I bring them to class the following day. And I take off the labels, so no one knows whether it's a Leo horoscope or Aquarius, or they just see the descriptions of how the day was supposed to have gone the day before. That was the horoscope for the day before. So I asked them to pick out, read them all, and they're random. I randomly shuffle them so that they're not in order. And I ask them to pick out the one that best described their day the day before. And so if horoscopes work, after they've picked these out, I tell them which horoscope they had, and if it was correct, if it was a match to when they were actually born, when their astrological sign, then we count it as a match. If it was a mismatch, we say, nope, you picked the wrong one. It wasn't the best predictor of your day yesterday. So match and mismatch. Those are the two things I look at here with this. I'm going whether they matched the prediction and their actual horoscope, the one that best described their day, or a mismatch. Okay. Now, would you expect 50% of the people by chance to get a match? No, because there are 12 different horoscopes. They're picking one out of 12. So if it was just random or by chance, you would expect the number of matches to be, if you just take 1 divided by 12 equals 0.083. So you would expect the match by chance to be 0.083. Okay? And then if you just take 1 and subtract 0.083, you get 0.917 for mismatch. So this percentage here, we're going to test how good our observed data fit this. Now you have to kind of think about what does this mean? If we were only to see 8% of our observations with a match and 91% or 92% with a mismatch, that would mean that it was similar to what you would get just by chance, just by shuffling them and not even reading the horoscopes, or not just taking one out and by shuffling all 12 and pulling one at random, just by chance. So we're asking the question, does our data fit this, our observed values, or if you get more observed values than expected in this match, so say we get 50% of our observed values with a match, then that would be support that the horoscopes might work. They might accurately predict their daily events. I have done this several times. I haven't yet rejected the null hypothesis, testing this goodness of fit. But this example I wanted to give you, you would then go collect data. If you had 100 students doing this, you would expect 8 of them. Your expected value would be 8. If you had n of 100, your expected value for match would be 8% of that 100, or 8 students, and or 8.3. Your expected value for mismatch of those 100 students would be the percentage expected, 0.917, times the 100, so you would expect to get 9.17. 9.17 for your mismatch. So those are your values. You can have decimals for your mismatch, even though you can't actually count 9.17 people, you still use it in your formula when you're calculating your chi-square. So then you would go out and take the information from these 100 people. If you ended up with a higher number of people, say you had 10 people up here out of this 100 that matched, 10, and then you had 90 that were a mismatch. Oh, there's fewer than I expected by chance to mismatch. But is it enough that would be significant? Or did you just find that little difference because of random error, because of sampling error? So that's where the test statistic would come in. You take the observed minus expected squared over expected, the observed minus expected squared over expected, add them together and calculate your chi-squared, bring it to your chi-squared distribution, compare it to your cutoff for the degree of freedom 1 here. We only have 2 categories, and you would decide to reject or retain the null based on this. If you reject the null, you say it doesn't match this chance. You retain the null, you say, oh, it's close enough to chance that the horoscope didn't accurately predict their day. All right, so that's just one type of chi-square. We need to move on back to the lecture. Let's move on to independence. So chi-square goodness of fit was for use when you only have one nominal variable with different categories. Now, and we're going to test when you have 2 nominal variables. So 2 different categorical variables, each with several categories, could have 2 categories, 3 categories, 4 categories. But the key here is that we're looking at, is there a relationship between two nominal variables, 2 different variables? And so here you want to create a contingency table. This is based on a contingency table. If you're not familiar with a contingency table, it's a table where you have rows and columns, and those break up whatever you're counting into different groups or categories. So the example I like to use here, we'll go to the drawing board. The example for a test of independence is we might ask the question, is there a relationship between the variable hair color and eye color? Okay, so we have 2 different variables now. They're both nominal, both categorical. Let's say, just for simplicity of calculating this today, I'm going to break up hair color into dark and light. Now, with the chi-square independence test, you could have blonde, brunette, redhead. That's fine. You could add all those categories in and it works just as well. But for sake of simplicity and explaining how this test works, I'm just going to have dark and light hair color. And I'm going to do the same with eyes. I'm going to have dark and then light eye color. So what it does is it's going to break up your counts, this contingency table. If I looked at someone in the class like myself, I go, okay, I have light hair. And then, so it's going to put me in this category of hair color. And then I go, okay, what color are my eyes? I have light eyes. Here's a count of 1. Now I look around the room and I go, okay, there's another student with dark hair, and that student also happens to have dark eyes. So we put a count of 1 there. And so then we continue counting, okay, here's another student with dark hair, but they have light eyes, and we put them in this category. So a contingency table breaks up information based on this row category or variable and the column variable. And it doesn't really matter which way you put these variables. It would mean the same thing as long as you know which variable is labeled on the column and which one's labeled on the row. Now, we're asking the question with independence, are these 2 variables independent? Or do they have something to do with each other? If they're dependent on each other, knowing someone's hair color would tell you something, the probability about their eye color. Or knowing their eye color would tell you the probability of their hair color. And so if they're completely independent, then knowing someone's hair color shouldn't tell you anything about their eye color. So if we have 20 people with dark hair, we should end up, if its eye color is not dependent on hair color, 20 people here, we would expect 10 to have light eyes and 10 to have dark eyes. The same thing with light hair. If hair color doesn't depend on eye color, if we had 20 people here, we'd expect 10 of them to have light eyes and 10 to have dark eyes. So there you can see our expected values. And our expected values are based on the idea that one variable is not dependent on the other, that they're independent, these 2 variables. And so we're testing, are they independent or does one rely on the other? And if here your null hypothesis is that they are independent. Okay? If you reject the null, you decide they're not independent. There is a contingency of one variable to the other. Knowing something about one variable tells you something about the other. So you see, just like the goodness of fit, you would go out, collect the data, take these people, put them in here. If the dark-haired people, we only had your observed values. Let's say for the 20 people, there were only 2 of those 20 and 18 of them, 2 of them with light eyes, 18 with dark eyes. So you have your observed values, and then of our light-eyed people, or light-haired people, sorry, we had, let's say, we had 19 of them observed with light eyes and only 1 with dark eyes. Then we just take that same statistic before, your chi-square statistic, where you take the sum of the observed minus expected squared over expected. So you do that for each of these, and you're going to add up each of the cells, the observed minus expected, so it would be 2 minus 10 squared divided by 10. In each of these, you add it up, and that's your chi-square test statistic. Once you get your test statistic, you need to take this test statistic and compare it to your chi-square cutoff. Now, let me move to the next slide. When you have a different number of people, so suppose that you had a different number of people with dark hair and a different number of people with light hair. You only have, instead of having 20 in each group, you have an unequal n for each category. Here, this is where you're going to need to use this formula for calculating your expected values. This formula in our PowerPoint just says that if you take the total counts in your row and divide by n, so it's giving you the percentage of individuals in your row, and divide by n, and then multiply by your column, that gives you your expected value for that one cell. And then you would do this for each cell. So for example, here's a contingency table with sleep tendency, morning and night, and then transportation, bus, carpool, and own car, and the counts. So you see at the very top row, 120 of the total sample have the sleep tendency of the morning. Okay? And so if you take 120, your row total, and divide by n, 200, your total n, you get 60%. 60% multiplied by your column total, 60, would give you your expected value from this calculation. So this is how you will calculate the expected values for each cell if you have an unequal n. The example I gave you was equal. We had equal numbers in each of the cells, so it was pretty straightforward. I wanted you to get the concept before I gave you the formula to calculate the expected values for each of the cells in your contingency table. All right. So now when you're calculating the chi-square, I already told you that it's exactly the same as the goodness of fit, observed minus expected squared divided by expected. Then you add up all of your cells, add up this value for each of your cells, gives you your chi-square value, how much of a difference you had in each of these cells accumulatively from your expected values. You take this chi-square test, where it says figuring chi-square, that's your chi-square test statistic, and then you have to compare it to your chi-square cutoff on the distribution. Now with a contingency table, your degrees of freedom are a little bit different. It's not just the number of categories minus 1, it's the number of categories for the row minus 1 minus the number of categories for the column minus 1. So you take the number of so if you go back to our last example here, you have morning and night, 2 minus 1 is 1. And then the top category, bus, carpool, or own car, you have 3 categories, 3 minus 1 is 2. It would be 2 times 1. You have 2 degrees of freedom here. So it's the number of groups in columns minus 1 times the number of rows minus 1. So that's where you get your degrees of freedom for the test of independence. Now, let's talk a little bit about assumptions for chi-square. You don't have the assumption of normality. Any idea why? Think about it. If you think about it, normality requires some continuous variable. Here you don't have a continuous variable anymore. We're only looking at categorical variables, counts and categorical variables. So a continuous variable testing for normality wouldn't make sense at all. So you do not have the assumption of normality. You do, though, have the assumption that individuals can only be counted in one category or one cell. Okay, so like with my example of male and female, each individual couldn't fit into both of those at the same time. They have to be mutually exclusive, the different cells that are broken up in your contingency table or in your goodness of fit. Okay, another example, the light hair and dark eye and dark eyes. One individual, you can't fit into more than one category. You can't be counted as light hair and dark hair at the same time. Each of those cells counts has to be independent of the counts in the other cells. Now, the effect size for a test of independence, a chi-square test of independence, if you have a 2 by 2 contingency table. So what I mean by 2 by 2 is that you have two levels of each nominal variable, two levels in the row variable, two levels in the column variable, only two groups for each of those, so you end up having 4 cells, just like the contingency table I showed you with hair color and eye color. If that's the type of test you're doing, then you would want to use phi as your effect size. And phi is very simple to calculate. You just take the square root of your chi-square test statistic divided by n, and that's your phi. And a small phi, or effect size for phi, is 0.10, medium is 0.30, and large is 0.50 or larger. Now, what if you have a table that has more than a 2 by 2? So for example, should we have used hair color and added, instead of dark and light, we use blonde, redhead, brunette, black hair. And so now you end up other pink, purple, maybe they have different colors of hair on there. So now we have not a 2 by 2, but maybe a 7 by 2. So if you have anything greater than a 2 by 2, then the effect size that you want to use for anything greater than this is Cramer's phi. And Cramer's phi is similar to phi, except you take the square root of your chi-square value divided by n times the degrees of freedom for the smaller category. So if you had a 7 by 2, then your smaller category, the degrees of freedom, would be 2 minus 1. It's going to end up being the same as phi. But if you have a 7 by 3 contingency table, so you have 7 groups of your nominal variable on the top and then 3 groups on the bottom, you end up taking and multiplying your n by the degrees of freedom for the smaller group, the 3 minus 1, which would be 2. So this is how you calculate Cramer's phi. And I just also have a table with the different effect sizes for Cramer's phi down at the bottom of the PowerPoint. All right, so just to review, the chi-square test statistics used for nominal variables, the goodness of fit is when you have one nominal variable. The test of independence, the chi-square test of independence, is when you have two different variables that you're asking if they're independent of each other or if one depends on the other. And you just calculate the observed frequency for each of those. You subtract the expected frequency that's theoretical based on what you would expect in there. You subtract expected from observed, square that value, divide by expected, add them all up. That ends up being your chi-square test statistic. Then you want to take this test statistic and compare it to the chi-square distribution. Just like before, depending on the degrees of freedom, your sampling distribution, the distribution of this test statistic, what you would get by chance, changes depending on how many degrees of freedom you have. So just like the T table that you've used before, the F table that you've used before, now we have a chi-square table that takes the test distribution and it calculates the probability of getting a certain chi-square test statistic at a degrees of freedom. This shows you what the chi-square distribution looks like at different degrees of freedom, 1, 2, 3, or 1, 2, 4, and 8. And you can see it changes as this goes. And you can see that the smaller your degrees of freedom, the closer or the more area there is closer to that 0, closer to the 1, because you're more likely to get differences in there when you have a smaller degree of freedom. So this distribution of the chi-square test statistic is where this table comes from. The information on this is just a little piece of your chi-square table. You have the complete thing in the back of your textbooks. So what you would need to do is you draw out the chi-square distribution, just like you've been drawing out the T distributions. You then want to mark your chi-square cutoff, which you get from this table. You first have to find your degrees of freedom. I've explained how to do that. You find your degrees of freedom. Once you've found the degrees of freedom right here, you are going to want to go over. So suppose you were testing 3 groups in a goodness of fit, then you would have 2 degrees of freedom. You would go over if your significance level, or alpha, was 0.05, then your cutoff level for your chi-square would be 5.992. Okay, if you were doing 0.01 alpha, your cutoff would be 9.211. Now your test statistic, you put your cutoff on your drawing, and then you draw your test statistic on your drawing of the distribution. If your test statistic is greater than your cutoff, then you reject the null hypothesis. You decide that the two variables are not independent of each other or that it's not a good fit. If your chi-square test statistic is lower than your chi-square cutoff, then you decide to retain the null. If it's a goodness of fit, you decide it is a good fit. It matches well enough. If it's an independence test, you decide that the two different variables are they are not, one does not depend on the other, that they are independent. And so that's the result of your chi-square analysis, your chi-square test, when you're using this table and the distribution to make that decision. All right. Let's take a look at how chi-square is reported in research articles. This is what you would typically see in a research article. Remember, the parentheses after the test statistic, it typically tells you your degrees of freedom. Here it tells you your degrees of freedom is 2. So if this was a goodness of fit, you would know that there were 3 different groups of that variable. So it gives you your degrees of freedom for the chi-square. It's 2 in the parentheses, your n equals 101. In this example, and then it says equals 11.89. That 11.89 is the test statistic. That's what they calculated when they took the observed minus expected squared divided by expected. They added those all up and they ended up with 11.89. Then they compared that 11.89 to the cutoff, and the p is less than 0.05. So if p is less than 0.05, that means that 11.89 was further than the 0.05 cutoff. It cut off a less amount of the tail than 5% in that tail. So you know that there's less than 5% chance that you would get that large of a test statistic, 11.89, just by chance. So they go with the rejecting of the null. They decide that it probably wasn't just by chance. If this is a goodness of fit, they decide, nope, it doesn't fit. If it was an independence test, they would decide that the two variables depend on each other. They're not independent. Okay. All right, so that's all we have for today. We've covered chi-square, goodness of fit, independence, how to do a chi-square, where the distribution comes from using the table, and I suggest you go through the homework problems, try a few. Chi-square is kind of fun, kind of intuitive, and I will see you guys next time.